Hello, let me first introduce myself. I'm Michal Janošek. I'm from the Czech Technical University in Prague, and I'm one of the three authors which are presenting this submission named Stabilized Magnetic Vacuum using a rotating Fluxgate sensor. So, let's go to the presentation. So let's talk about the motivation for just another magnetic vacuum system. The magnetic zero or magnetic vacuum which we can create in a coil system. Basically you can see one of these coil systems in the picture on the left hand side. The magnetic zero can be really useful for experiments in paleomagnetism, for example, estimate on the age of the rock samples. But of course, it's not only this special branch of science, it's also very useful for any calibrations of magnetic field sensors. The benefit would be once we establish a true zero and once we know the coil constants of our coil, which can be estimated really precisely, we can have almost perfect calibrations which would not depend on the Earth's magnetic field changes during the day. Of course, there are systems which are already operated. I call them heritage systems. They are quite stable. They are using rotating coils, but because it's really mechanical, and the coils of course have to rotate at quite high speed, so they are really noisy at 1 kHz. Moreover, because it's based on Faraday induction law, the voltages are very small, so it's also very susceptible to noise in the baseband. So let's say any EMI which would appear just from 0 to 1 kHz would be induced in your coils and would interfere with your measurement. So there are also feedback compensated systems which are using, let's say, Fluxgate sensors or AMI sensors from the two vectorial sensors available, but those two sensors suffer from zero, from the offset, and from the temperature drift of the offset. It's possible to calibrate for them, for example in magnetic shield, but these two parameters are really not stable in time and with temperature. There are many other systems which allow you to create a non-zero field based on atomic sensors, but again the issue is once we want to create a zero field, we really need to use either Fluxgate sensor or AMR sensor. So let's take a look at our solution with a rotating Fluxgate or AMR magnetometer. So our magnetometer will rotate in a plane, and with the help of the rotation, the remanence and the sensor offset are constant. They do not change during the rotation, but the field, the, let's say, outside field, which is not mechanically connected to the rotation, will be modulated, and the amplitude of this field is the amplitude we want to compensate by applying magnetic currents in our coils. So these coils we will just counteract the Earth's field and any changes of the Earth's field during the day or long term. We can introduce 2 points or 2 reference marks which will just serve for the modulation of our modulated signal, so that we can get 2 components, the in-phase and quadrature, or if it's well aligned, the coil system, we can get the north-south and east-west component. The other point is we can also tilt a little bit the plane of rotation by the angle beta, and then we are not only compensating for the horizontal component of the field vector, which can be like this, but we will also compensate for the vertical component of the field vector. In the extreme variant, of course, we will tilt our sensor, we will tilt the rotation plane just by 90 degrees, and then we are sensitive only to the vertical axis. So let's explain the principle a little bit on the real data which we acquired during the Fluxgate sensor rotation in the horizontal plane. So this is the very basic equation which shows us how the field gets modulated. So this is the ambient field, BA, this is the rotational frequency, this is the sensor sensitivity, and this is the offset. And we can see that the only time-dependent component is that one which is related to the ambient field. The sensor offset is stable in time. And even in the graph we see that this average value is the sensor offset. We do not have to regard it. And our test field, in this case 6 nanotesla, results in 12 nanotesla peak modulated signal. So the only thing we need to do is either establish the peak value or just demodulate with the help of the reference marks. So let's take a look at the breakdown of our Fluxgate magnetometer, which is rotating. So the components are the Fluxgate sensor here with number 1. Then we have the analog and digital, the analog to digital converter and the wireless module for transferring the digital data. Of course, we have the magnetometer electronics, which is demodulating the Fluxgate signal and providing us with analog values. We have the reference optical sensor, which is just this one. This is also attached to the plane, and during the rotation with 2 reference marks, which are just aluminum plates here, it provides us with those 2 M1 and M2 markers which we are using for the modulation. And of course we need to power the setup with a LiPo battery, which is also only slightly magnetic. But once more, the magnetism on the platform is not an issue because it's constant with reference to the Fluxgate sensor. When it's rotating, again, it doesn't move relatively to the Fluxgate sensor. And the other question will be the soft magnetism, but since we are trying to establish a zero field, we will not have any soft magnetic effect. Let's take a look in detail on the rotating parts. So either we have our Fluxgate magnetometer here, or we were using later on also a triaxial anisotropic magnetoresistor. In the next slide we will quickly see a slow motion video of the rotating magnetometer in the coils. Let's run it, and what you will see will be the belt driving it and the reference sensor here. Okay, let's take a look more into the details of the compensating system, because it's not only the magnetometer, it's also the current source which is driving our coils. It's the LabVIEW software. Here we have a little screenshot of it, and we have utilized also the so-called auxiliary magnetometer. This one is placed outside of the coils, not inside, and is used only to sense the changes in the Earth's magnetic field, so that we once we establish the zero in the coils, so that we can compensate on the changes in the Earth's magnetic field and we can keep the zero stable. Once more we are using the ESP8266, this is error, and ADC for the wireless transfer of the data to our data acquisition in a PC, which is providing us with a graph. And just now in the current version of the software we are tuning the coil currents manually to create the zero in the coils. So let us take a look at some of the results. We are showing here 15 minutes of 0 nanotesla stabilized to plus minus 1 nanotesla, and we can see that even there was a car parking which was causing quite a big shift in our auxiliary magnetometer. This one was not placed in the coils again. So with the help of this auxmag and the compensation algorithm, we could really suppress even this quite big 7-8 nanotesla change in our coils to, let's say, below 2 nanotesla. We see these peaks here, which are about, I would say, every 2 or 3 minutes. These peaks are due to the ESP module Wi-Fi calibration, so this is not an actual magnetic disturbance. We developed a new version of the rotator. It's completely non-magnetic, it's 3D printed, and it's a differential-like assembly. So with those 3-toothed wheels, we can rotate our platform in one axis, and we can also tilt the platform in the second axis. The Fluxgate sensor will be sitting here in the 3D model, and in the real printed and operating mock-up, let's say just now, this is the Tic-Tac box just simulating our Fluxgate. So now it's time to go to conclusions and our promises for the future. So we created a system with a rotating Fluxgate or AMR, with a wireless transfer and acquisition, and with the help of another magnetometer, which is auxiliary and outside of the coils, we can find or establish a 0 and stabilize the field. Then we can of course take the rotator out of the coils, and we can place a device under test in our coils, so we can calibrate in 0 fields, or we can also preset other fields very precisely. We have achieved 1 nanotesla residual field, and of course if we go to larger coils, we think we will have better results because of higher homogeneity. And we have seen the new version of the rotator, and this will allow us for easy compensation of horizontal and vertical field components at once. And we are really looking forward to install it finally at Saunderson in South Africa in their 2.5 meter coils to achieve much better homogeneity. So once the traveling is possible again, we will report how we are progressing. Thank you for your attention.